I thought it could be perhaps the occasion to talk about some work we did with 4 co-authors from Charles University in Prague on inclusion-exclusion. So I will try to keep the talk not too technical. I think it's perhaps better to just tell the story. These inclusion-exclusion formulas, they give rise to some interesting interaction between combinatorics, topology, and probability. And so that's what I would like to explain, how these things relate to each other. So let me start by recalling what the inclusion-exclusion principle is. And by the way, all the things I will talk about today, you can find them in a paper on the archive called Simplifying Inclusion-Exclusion. So if you want some details, you can just start by looking it up. So the inclusion-exclusion principle is assume F xn. So assume you have a family of sets, a finite family of sets, finite set. And you want to count how many objects are in the union, and that's complicated, but you can easily count how many objects are in the intersections. And the inclusion-exclusion principle simply relates the size of the union to the size of the intersection. So the idea is simple. You can start by counting, by adding the size of the object, but then you overcounted whatever was in the intersections, so you subtract it. But then you undercounted whatever was in the triple intersection, so you add it again, and so on. And what this says is simply that the size of the union or I of the xi, it's a sum for all possible subsets of n of alternating size of intersection. Okay, so if you specialize,
so the empty set is not counted.
The empty set is not counted. So if you specialize for the case of 2 sets, this simply says that the size of the union of x1 and x2 is the size of x1 plus the size of x2 minus the intersection. Okay, and if you look at the size at the case of 3 sets, well, then you're simply saying that x1 union x2 union 3. So you sum the size of the set, you subtract the pairwise intersection, and now if you assume you have an element here in the intersection of all 3, you counted it 3 times here and you subtracted it 3 times there, so you have to add it back. Okay, and if you want to prove this principle in general, it's very simple. You can pick a point in the union and you evaluate those 2 terms. You evaluate, in fact, the indicator function of this union in that point and the indicator function of this intersection, the sum of the indicator function of this function in that point. And what you will get is you can pick a particular subset, those of the indices I, such that V belongs to xi. And now you need only look at the sum for I subset of j. And for all those, this indicator function will evaluate to 1. And so the condition will tell you that the will be the same as saying that for any V, the sum for I different from the empty set and contained in GV minus 1 times size of G of I plus 1 times 1 is equal to 1. And this simply follows from expanding 1 minus 1 to the size of G of V. Okay, you expand this, you find all those terms, and this will be equal to 0, but in this expansion there is a term corresponding to the empty set, precisely, that will be equal to this one here. Now, this principle, you find it in many textbooks. It's very useful. It's useful in combinatorics when you want to count objects that, for example, have a certain property, and it's easy to identify objects that miss the property. Okay, for example, if you have a graph and you want a dominating set, it's easy to say that a set of vertices is not dominating because it doesn't touch this vertex. And so you can perhaps count all the sets that are not dominating because they miss this vertex or that vertex or that vertex. But then if you sum them up, you are overcounting the number of non-dominating sets, because a set that is not dominating might miss one vertex and another, so you count it in both terms. And so you can turn, you need to use inclusion-exclusion principle to count things correctly. It's also useful if you want, for example, to estimate volumes of simple shapes in computational biology. You usually represent a molecule as a union of balls. If you want to represent the accessible volume, often a good approximation is a volume of the union of balls. And so to compute it, it's often easy to compute the volume of intersection, and you use inclusion-exclusion principle for the union. It's also used in probabilities and so on. I forgot to mention it, but if you have questions, you feel free to ask them, online. But as soon as you move to this more algorithmic application, there's really one big issue with inclusion-exclusion. And that issue is that you have potentially an exponential number of terms here. And that means that if you want really to apply inclusion-exclusion to compute the volume of a family of balls like this, going through all those subsets would be very inefficient. You would be doing 2 to the n computation if you have n balls. And that's not good. So one question is, could we possibly simplify? And I'll come back to this later, but essentially if you want a formula that is exact in the sense that this here is an equality, it's not approximately equal or of the order of magnitude of, it's an equality, and your formula works for any collection of sets, this is the only formula that will work. This is the only solution. But if you're willing to compromise on either the exactness of the formula or on its universality, then we can do something. So let me quickly sketch. In this talk I will talk about relaxing uniformity. So you give me beforehand a set system, and I want to compute a formula that will work for that set system. But before I get to that, let me quickly sketch what you can do in terms of approximation. So there's one approximation of the inclusion-exclusion principle that everybody knows, right? It's the union bound. It's if you just sum the size of the set, you get an overestimate on the size of the union. Union of the xi. Okay. What is the next step? Well, you can simply pick this formula and truncate it at any level you want. So, and depending on whether you truncate at an even step or an odd step, you get an over approximation or an under approximation. So, for any r, so the union of I in xi is less or so if you limit the sum to subset of size at most r, then when I is odd, when R is odd, you get an upper bound, and when R is even, you get a lower bound. And these are called Bonferroni inequalities. And now you can actually start relaxing a bit the type of formula you look at. For the moment, we only looked at formulas where we want to bound the union as a sum of measure of intersection, where the coefficients are simply -1 to the cardinality +1. What if I relax this and I allow any linear combinations? Then you can have what's called Bonferroni type. Formulas. For example, there is one due to Galambos, 1975, which says that here, if you replace the coefficient of the last term, if you multiply the coefficient of the term with maximal cardinality by r plus 1 over r, so you make the coefficient smaller. Okay, so that means you start with a union bound, and when you remove the pairwise intersection, you actually remove 3 over n times the size of the pairwise intersection. So you are correcting less than what you do here. That is still enough to guarantee that you go from an upper bound to a lower bound. Okay, so union bound is here. When you remove the pairwise intersection, you get below the actual value. You can actually do a smaller jump, and that's still correct. So let me just write it. The union is still larger than the sum of the xi minus 3 over n times the sum of the xi xj. And so Bonferroni observed this inequality in 36, and since then there has been really a lot of activity on this. You can find books called Bonferroni type inequalities. There is really a large activity there. And so perhaps one question that comes to mind is how good can we do? So if we are willing to allow arbitrary coefficient not just on the last term but on all terms, and we fix a size, so we want to go to all k-tuples, intersection of k-tuples for k up to r. How good can we do? So fix r, consider a formula of the type sum for all I in n of some lambda I times the size of the intersection of the xi. So how far can this be from the size of the union? In the worst case, when I'm allowed to design the family after fixing the coefficient. I mean, could there exist some constants that work well for all sets, that work not too bad? And so this was studied by Lignal and Lignal and Nissan, and Kahn, Lignal and Samoroniski. And what they essentially show is that if you want a reasonable error, you need to have R of order of magnitude root n. Okay, if you take something much below that, then no matter which coefficient you choose, there will exist set system for which this formula will be a bad approximation. Okay, so I don't go into the technical details how actually what bad means, but the bottom line is even if you want to approximate, you still need to look up 2 to the root n terms. So that means that approximation won't solve the problem if you really want, for example, polynomial time computation. So instead of studying approximation, what we looked at with those colleagues from Prague is ad hoc formulas. So the setup is slightly different. So you give me in advance the set you want, the set of the xi, and I will try to compute a formula that is correct for that set system, and that is small. And what makes this possible? Well, let's consider this set system. So I have set 1, 2, and 3. And if I look at the inclusion-exclusion formula, I have essentially 1 plus 2 plus 3 minus 1, 2 minus 1, 3 minus 2, 3 and plus 1, 2, 3. But now if you look at the intersection of 1 and 3, it's covered by 2. So that means that these two terms, they are equal. As soon as the set intersect in this way, those two terms are equal, and since they appear with opposite sign, I can just remove them. And so for what I'm saying is for any collection of 3 set, so that the intersection of 1 and 3 is covered by 2, I can compute the volume of the union by applying this formula. Okay, and this was observed by Kratzky, a physicist in the late 70s, who used this principle to show that whenever you're looking at an intersection of balls, you can always write it as an inclusion-exclusion formula of intersection of at most quadruples of balls in 3D. And so quadruples of balls are nice because you can give an actual closed form formula depending on the distances between the centers, and that physicists were happy with. And now the idea is the question is how could we study this more systematically? What kind of structure should we look for, and how should we describe that? How can we describe that? So let me introduce 2 different creatures. So I have a family F of sets. So I introduce the nerve of F. So it's simply the set of all subsets of F that have non-empty intersections, that have a point in common, that have something in common. Okay, the intersection okay, so here the nerve would be so here the nerve, well, I have all the singletons, then I have all pairs, and then I have the triple 1, 2, 3. Okay, so it's just a collection of subsets. And I define also what we call the Venn diagram. And it's slightly different. It's a subset of these. It's the set of all subsets such that the I want not only the intersection of the elements to be non-empty, I want actually it not to be covered by the remaining elements. Okay, so the union so a family G is in the Venn diagram if there is some element that belong to all the members in G and nobody else. Okay, and so here the Venn diagram, well, this is in 1 and nobody else, so I get 1. This is in 2 in nobody else, this is in 3 in nobody else. I will get essentially all those regions with the exception of 1. I will not get 1 and 3 because everything that is in the intersection of 1 and 3 is also in 2. It's covered by 2. Okay, so the Venn will be the nerve minus 1, 3. So in both cases, it's clear that the nerve of F and the size of the Venn diagram of F are both less or equal to 2 times the size of F. Okay. Okay. Now, the main theorem we can prove is that any such system has an inclusion-exclusion formula whose size can depend on is adaptative in the size of the Venn diagram. Okay, so let F be system then this and so this formula has the same nice structure as the inclusion-exclusion formula, so the coefficient of each intersection is simply -1 times the cardinality, and the size of the subset is bounded by, so only subsets size to log m times log n over log m. And let me make a big O here so that I don't have to worry too much about the constant. Okay, so recall that m, so here m can be up to 2 to the n. So if I plug 2 to the n here, what I get is so in fact times, if I want to discuss this, it's perhaps better to do that. If I plug m equal 2 to the n, this disappears, this is 1, and I get n here. So I'm just saying the formula will have size at most will use subsets of size up to 2n, so that's trivial, but it captures the right order of magnitude. Now,
I missed what is the definition of a formula?
Of?
What is a formula? What are these lambda subset of?
Okay. So here, what I mean.
You've written something there. Consider a formula. So maybe you can just tell me here.
No. So, okay, what I mean here is, okay, there exists a simplicial complex okay, whose simplices have this dimension at most,
yes,
and such that the union of f is equal to the sum over all simplices of k that are non-empty of -1 times dimension of sigma times size of the intersection I in sigma of xi. Okay, so I'm really starting from the complete inclusion-exclusion formula, and I'm deleting terms. And what I'm saying is, it's always possible to delete terms and keep only terms involving subset no larger than this. Okay, that's what I mean by a formula.
And it's going to be exact.
It's going to be exact, but it's going to be exact for this f.
Sure.
Okay, and so it's always possible to simplify by some amount, and this amount is parameterized by the size m of the Venn diagram. Okay. In the worst case, if m is 2 to the n, we get it. But actually, when the Venn diagram has size 2 to the m, there is no other formula than the complete inclusion-exclusion formula. Okay. And so the idea here. So that's the main result. It's to have this kind of adaptative type of formula. So this type of research was the first result in this direction. It's due to Neyman and Wynne. What they did is try to take a set system and construct a combinatorial object, perhaps a graph, perhaps a chordal graph, perhaps a simplicial complex like this, that induces a formula in this way. And they could do it for two types of objects, so half spaces, RD, and families of unit balls. And the result they obtain here is actually beautiful. If you have a family of unit balls, what you can do is simply compute the Delaunay triangulation of the centers. You view that as a simplicial complex, so you consider the set of all the faces of the Delaunay triangulation, and you take the inclusion-exclusion formula over those defined by those simplices, and it will be correct. Okay, so if P is a point set, if K is the Delaunay triangulation of P seen as a simplicial complex, then the measure of the union, right, of the ball centered, so for P in with radius r, so you fix a radius rho. This is equal to the sum for sigma in K of -1 times the dimension of sigma of
So this contains the result of that physicist you mentioned?
No, because the physicist was merely, yes, he had the coefficient here that can be other than +1, -1. because what he was just doing is say this intersection is equal to that intersection. You substitute, and perhaps they have two sizes of differences, and so then they would add up. He would simply say that the larger is equal to the smaller, and so you can just delete the larger and put 2 as coefficient for the smaller, and so you would have integer coefficients. Yes, counting is volume. Yes. So I'm not too careful about that because everything that I'm saying is true for indicator function. So it's true for any integration of an indicator function. Okay. And so this is the type of result that is actually nice because you don't have to actually compute the Venn diagram of those sets to compute the sparse inclusion-exclusion formula. Right? You just get an inclusion-exclusion formula here that is very sparse because it doesn't take subset of size more than d that I mentioned, d plus 1 I mentioned, and you can compute it very easily given the sets. You don't actually have to understand how they intersect. That is embedded somehow in the computation of the Venn diagram, of the Venn triangulation. Okay. And so what we are mostly pointing out is that such simplification exists in general. We can give an algorithm to compute them, but the algorithm starts from the Venn diagram. So in many situations that is quite expensive to compute. So it's not so exciting, perhaps. But so how much longer do I have? Maybe 20?
25 minutes.
Okay. So by the way, everybody is clear on what a simplicial complex is, or are there? Yes? Okay. So how do we prove that? So we start from a simple necessary condition. So let F be a subsystem. Let K be simplicial with vertices. So I'm taking really a simplicial complex with vertex at F. And now, if no face of the Venn diagram of F is minimal, is a union So assume that every time you pick a face of the Venn diagram, you cannot describe it as a union, not necessarily a disjoint union, just a union of minimal non-faces of the simplicial complex. Then K define a correct formula for the family F. And what this means is that okay. So the way we can prove this is by topology, some topological consideration. Specifically, So the condition that the formula is correct is simply that, so when you have your collection of sets here, and you're looking at this formula and you want it to be correct, what you can do, again, as I did earlier, is pick a point here and check that the formula is correct when you replace here this by the indicator functions and when you evaluate it in that point. Okay, so we ask the following: is
Minimal non-basic is with respect to inclusion.
minimal with respect to inclusion? Yes. Okay, so we can simply rephrase the question in these terms. Is the indicator function of the union equal to the same linear combination of the indicator function of the intersections? Okay, so this is true if and only if it is true in every point. So I will simply check it in each point. So I pick.
Can you give some example? Like I'm still confusing. Like bases are like vertices are a sets, right? In the set system.
So here.
Yeah. And bases are.
Yes. So
set of sets. Right?
so it's yeah. So I have F.
A concrete example.
Okay. So assume that F is this. Then I'm going to assign to each of the set a vertex. Okay. On that I will construct a simplicial complex. So it can be this, for example. So okay, let's just take this. So on these three examples, I take this simplicial complex. Okay.
It doesn't correspond to the example.
I didn't say K. I mean K is an arbitrary simplicial complex. I didn't say it's a nerve.
An arbitrary simplicial complex. Oh, okay.
Any simplicial complex. Okay. So I could actually take. Let me take an example that doesn't work. Let me take this. Okay, it's a simplicial complex on this set. And now, what I'm looking at, what I'm saying is, pick every face of V. So the Venn diagram. So the faces of the Venn diagram correspond to this region here. Okay, all these points correspond to this thing. So if this is 1, this is 2, this is 3, I'm looking at vertex 1, vertex 3, vertex 2. And this will define for me the formula 1 plus 2 plus 3 minus the intersection of 1 and 3 minus the intersection of 2 and 3, and that's all. Okay, so this simplicial complex defines this formula. Okay, and the question is this formula equal to 1 union 2 union 3? So what we can do is pick every region and check that the formula is correct over that region.
So inclusion-exclusion is when K is the full simplex.
Exactly. Mm-hmm. And if you trim down the inclusion-exclusion...
So long you don't make faces of this thing.
Yeah, and if actually you start with a full inclusion-exclusion and you remove all the intersections that are empty, you're simply taking K to be the nerve. Mm-hmm. Okay, so... And if you make a simplification of the inclusion-exclusion formula and make sure that it is monotone, so if you have a collection of terms, you have all the subset, you're basically taking a subcomplex of the nerve, or of the full simplex. So what happens here? If we evaluate it here in this point, well, the union should be counted once. But here, we're counting, so this evaluates to 0, this evaluates to 0, this evaluates to 0, this evaluates to 0, this evaluates to 1, so we are happy. Now, what is happening is, if we take something in the intersection of 1 and 2, 1 and 2, this evaluates to 1, this evaluates to 1, so that evaluates to 2, but I don't compensate it. So that will be wrong. And if I take 1, 2, it is a face of the Venn diagram, and I can describe it as a union of minimal non-faces of the simplex, namely 1, 2. 1, 2 is a non-face of the simplex, and if I remove anything from it, I get either 1 or 2 that are faces. Okay, so this is what actually this is a sufficient condition to determine whether a simplicial complex gives you a correct formula or not. And one way to see it is to move on to this indicator function, to pick a point V in the union, but when you and check that the formula is correct. When evaluated in V. But now if you take two elements that, so the region of the faces of the Venn diagram correspond to those regions, and they define a partition of the union into cells. Okay, so for each point you look at all the elements that contain it, and that set of elements define a face in the Venn diagram. And so this will correspond to a face of the Venn diagram, this will correspond to a face in the Venn diagram, and so on. So it's sufficient to check that it's sufficient to take one point in each region, in each such region. Okay, so okay, and what this means actually when you translate it is that pick a region in the Venn diagram. So I pick a face in the Venn diagram. Now the region, and I pick a point in the corresponding region. So the corresponding region is the intersection of everything that is in tau minus the union of everything that is not in tau. Now I evaluate. What do I get? So this should be equal to 1. What does this evaluate to? Well, all the intersection, this indicator function will evaluate to 1 if and only if sigma is contained in tau. Okay, so this should be equal to the sum and perhaps you recognize something. This here. Did I write it correctly? Sorry.
How many?
Tau, and also I want sigma belonging to K. Okay. So this is the same as the sum for all sigma, again pure non-empty, in the induced subcomplex of K on tau of -1 times the dimension of sigma. And this is simply the Euler characteristic of this induced subcomplex. Okay, you're summing, this is the alternating sum of the number of faces of all dimensions. Okay? Now, let's go back to this criterion. Assume that this condition, assume C holds. So what I want to show is that every time, so my complex K satisfies this condition. What I want to show is every time I take a face of the Venn diagram, I look at the induced subcomplex by K on that face, the Euler characteristic of that subcomplex is 1. I will prove something stronger. I will prove it is actually contractible as a subcomplex. And so because Euler characteristic is invariant under homotopy, this will mean it is 1. Okay? And how do I prove that it is contractible? I prove something even stronger. I prove it is a cone. So it has an apex. There is a vertex that such that if you take anything in this subcomplex and add the vertex, you are still in the subcomplex. Okay? So and this vertex is what? It's whatever is not covered by the minimal non-faces. So I pick tau in the Venn diagram. Let A tau not okay. So now what I want to claim is if sigma is in K tau, then sigma union A is in K tau. Okay. Every time you have a face, well, so if it contains A, I'm not saying anything. That's trivial. But if it doesn't contain A, I can look at the simplex spanned by this face and A, and it will also be there. And that means that would imply that K of tau is a cone, which would imply its Euler characteristic is 1. I know this is easy because if assume sigma belongs to K of tau and sigma union A does not belong. Okay. Well, what could happen? It could be that this is not a faces of K. I mean that means that this is not a faces of K. So K union. So let me take a minimal non-faces of this. A minimal non-faces of K that is contained there. So it could be this, or it could be something smaller. So if it is something smaller, if it does not contain A, it's contained in sigma. But sigma is in K. So it must contain A. Okay? Did I lose everybody? So let me just spell it out. So let beta be again, minimal is with respect to the inclusion. So this beta, I know that there is one because it could possibly be sigma union A, perhaps something smaller. If beta is contained in sigma, I get a contradiction because sigma is in K. So beta cannot be because so beta contains A, but that contradicts this assumption. Okay, so I started by assuming that I had a sigma in this such that the union with A is not there. I get a contradiction. There is no such pair and the claim is true, and all such induced subcomplexes are cones, and they all have a characteristic 1, and so this equality always holds, and so this identity between characteristic function holds, and so this proves my necessary condition. Okay? So what can we do with it? So perhaps I'll keep it. We use it as a way to generate many formulas randomly. We use it as a way to generate a random formula, and we show that on average the probability that one of the formula we generate has low dimension, in the sense is generated by a simplicial complex of low dimension, is positive, and that will be enough. Okay? So the idea now, we generate random simplicial complexes. And the way we will do that is we will make sure that we generate only random complexes that satisfy the condition. This condition C. Then we will show that the random simplicial, so let me generate a random simplicial complex K. We show that K contains a large, no large simplex with positive probability. And so this is enough to guarantee that there exists one such complex. Okay, that's the probabilistic methods.
How do you generate a random simplicial?
Yes, I'm coming to that. Okay. So if you're looking at this criterion, what it tells us is that for every time we pick a face of the Venn diagram, there is some vertex of that face that witnesses that it's not covered by the minimal non-faces. Okay? So what I'm going to do is I fix a selector. What I mean, this is an application S that goes from the Venn diagram to F, and for every face tau, I map it to some vertex in tau. Okay, so for each face in the Venn diagram, I mark one vertex, and I will want this vertex to remain uncovered by minimal non-faces. If that is true, then I know that the complex that satisfies this is good. It will satisfy this condition. So from this selector, now I have a set. I have a set of candidates, the candidate minimal non-faces. Okay. So if sigma in, so assume this, I want this to be a minimal non-face. What condition should it satisfy? only if, well, when for any tau in the Venn diagram, if sigma is contained in tau, then S of tau should not be in sigma. Okay? So what I'm saying is, now I only allow sigma to be a minimal non-phase only if, well, I make sure that this condition is true. So any tau in the Venn diagram that contains sigma, I should not cover the width for tau by this sigma. Okay? So I collect all such candidate minimal non-phases, and I pick the smallest possible anti-chain, and that gives me the complex. Okay, so what I just described is how, if I fix a selector, I can generate a simplicial complex that will clearly satisfy this condition C, because the selector will tell me so. The selector will tell me pick any face of the Venn diagram. The vertex selected by this face will not be covered by the minimal non-faces of that complex. Now all we need to do is to generate randomly a selector. And that we can do easily, because one natural way is we pick a random order on the vertices, and for each face we select the smallest vertex for this order. Okay? So that gives us a way to generate simplicial complexes that satisfy this condition. And perhaps in 2 sentences how the upper bound can follow. With this type of selectors, if we have a large simplex, that means that that gives us a very particular structure in some incidence matrix. So we pick a random order on F, define selector to be mapped to the smallest element with respect to that order. We get a simplicial complex. And now a large simplex will give us a certain pattern in the incidence matrix between the Venn diagram and the set. We'll give a pattern in a permutation Okay, so we have this matrix where the lines correspond to the elements of F and the columns to the elements of V of F, and where I have a 1 if the element is inside the face. And now, by looking at the permutation of so when we look at the column, so this induces a permutation of the column, and in the permutation of this matrix, we can show that a large simplex in that simplicial complex will induce a certain structure there. Some column will have to have 1 in certain orders and so on. And that we can analyze probabilistically and show that the probability that this happens when the simplex is large enough is sufficiently small that the probability that no such thing happens is positive. Okay, and that in a nutshell is the essence of the proof. Okay, and I think I should stop here.